All right, our last set of notes for this test is the derivatives of exponential and logarithmic functions. All right, so first couple of slides, okay, just like last time, we're going to talk about why is the derivative is what it is. If you want to skip this, okay, I guess you can do that and get to the actual problems. All right, so here we have the exponential function y is equal to the x power. Okay, and over here, somebody has graphed the derivative. Okay, now what can you tell about both of these two graphs? All right, well they're almost the same, right? Okay, there might be a little bit different. It looks like this one is maybe a little flatter, doesn't quite rise as fast. If you get what I'm getting at, okay, it's kind of flatter for a longer period of time than this one is. All right, but it still almost looks like the exact same functions, correct? Okay, and the reason why is because again, let's talk about what the derivative function does. It takes slope values from the regular function, okay, and it turns them to y values over here. All right, so as I'm going off to the left on this graph, the slope values are what? Very, very flat but positive, and they're almost zero. Okay, so over here on the derivative graph, as I go to negative infinity, my y values are positive but really, really close to zero. All right, and then as I go over to the right, my positive slopes start increasing and then start increasing very, very fast. So this slope right here is very, very steep. Okay, so it's a very, very high number as far as the slope. So when you graph the derivative, those y values are all positive, okay, and they get positive very, 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 very fast. Okay, so it's almost like as if the function and the derivative are exactly the same. And they're almost, it's very, very close. All right, here's the actual formula, or here's the actual derivative of an exponential function. Okay, exponential function, if you have a, well, I guess we should talk about exponential function. An exponential function is a function, it kind of looks like x squared, x cubed, x to the fourth, except the variable and the number switch places. You have the number on the bottom as the base, and the variable as the exponent. Okay, and for this one, for exponential functions, the base has to be a positive number. Okay, if not, weird things happen with negatives, and it's not a function. It's not continuous, at least. All right, so if you take the derivative of an exponential function, you get the exponential function back times the natural log of the base. Okay, and so that's why that function on the previous slide looked almost exactly the same, except for it wasn't exactly the same. Okay, remember we talked about that. So it's still an exponential function. It just has a constant, which on that rule has it at the end. But you can kind of think of this as a coefficient you can put in front, which would be a vertical stretch or shrink, okay, depending on how big that number is. All right, so let's look at a problem that deals with this. Okay, if the value of a $100 investment doubles every year, its value after 2 years is given by this formula right here. The value of t, again t, this t stands for time, is 100 times 2 to the t power. Okay, that's not 1,002 to the t power. You know, there's a little break there. All right, find an instantaneous percentage rate of change of the worth. Okay, so again, this little statement right there, instantaneous rate of change is your derivative. Instantaneous is your derivative. All right, so if the v of t is equal to 100 times 2 to the t power, we're going to take the derivative. That's pretty simple. Okay, v prime of t. All right, there's a coefficient there, so I'll leave the coefficient, 100. All right, I even rewrite the exponential function, 2 to the t power. And the only thing I have to do after that is look at the base and write the natural log of that base. That's it. The derivative of the value function, or the instantaneous percentage rate of change, is 100 times 2 to the t power, the natural log of t. Couldn't be much more simple. All right, now that we've done one example with a base of 2, okay, you could use any base you want to, all right, depending on the problem. All right, but the most commonly used base by far in mathematics that's naturally occurring is the irrational number e, which we talked about last year. E is 2.718 dot dot dot, kind of like pi, keeps on going forever, but it never stops. Okay, and remind me sometime to tell you where that number came from. It's actually a limit problem with some nested fractions, which is quite interesting, but we won't talk about it here. All right, but e, why is this so nice in calculus? Okay, it's because we remember that the natural log and the e function, okay, are inverse operations, like multiplying and dividing. Okay, squaring and square rooting, they undo each other. So if you have the natural log of e, okay, to the x power, the natural log of the e just cancel out and the x is there. Okay, or if we leave the x off, okay, the natural log of e is just equal to 1. All right, so when we take the derivative of e to the x, using that derivative rule we just learned previously, we have e to the x times the natural log of e. The natural log of e is what? 1. So we have the derivative of e to the x is just, in fact, itself. E to the x, its derivative is e to the x. So we found the 100th derivative of e to the x, you'd still have e to the x, which is quite nice. So I'm going to leave this here. All right, so just a little math humor, just saying that the derivative of e to the x, if you try to differentiate e to the x, it's not very effective. All right, so before we do some more problems, we need to talk about the chain rule with exponentials. All right, if u is some differentiable function f of x, I'm just using a little bit different notation here, then I have a to the u power, and I want to take the derivative of it. Okay, it's the derivative of the outside, so a to the u. Derivative of a to the u is the a to the u times the natural log of a. And then you also have to remember the inside is now the exponent part, so we need to take the derivative of that. And that's what du dx stands for. Okay? So again, it's just the normal chain rule. Okay, just remember, for exponentials, you rewrite the exponential, the natural log of the base. All right, and then with the chain rule, you can also find the derivative of the exponent. Okay, and so when we do that with the e to the u, that special e, then all you have, the derivative of e to the u is e to the u times the du dx. Okay, or little, so you can help you remember it, the derivative of e to the u is e to the u du. E to the u du. Should be easy to memorize. All right, so let's look at a couple problems that use that. All right, my first function, f of x, is equal to 3 times e to the x squared power. So we take the derivative of that. We have 3, which is just our coefficient. We have the derivative of an exponential. So in the base is e, so we have e to the x squared. Just write it down. That's the derivative of the outside. All right, and then we also have to multiply, since the exponent is not just x, it's x squared. We need to take the derivative of x squared, which is 2x. Clean it up a little bit, and that gives you 6x times e to the x squared. Pretty simple. Okay? Rewrite the exponential, and then take the derivative of the exponent. All right. For the second one here, it's a little bit more complicated because we have product rule. All right, so let's do it. Product rule. When we take the derivative, which will be y prime in this case, we take the derivative of x. What's the derivative of x? Just 1. So really that first one is just 1 times e to the 2 over x power. All right, plus, leave the x alone, and then take the derivative of the exponential function. So we have e to the 2x, and then we need to multiply that by the derivative of the exponent. Okay? Well, the derivative of the exponent, let's rewrite that exponent as 2 times x to the negative first power. When we take the derivative of that part, I'm just kind of thinking out to the side. Well, that's equal to a negative 2, because the negative comes down. And I subtract 1 from the exponent, so I get an x squared on the bottom, or x to the negative 2. So it gives me times a negative 2 over x squared. All right, and so when we clean that up a little bit, we end up getting that the y prime is equal to e to the 2 over x plus, not plus, we can actually bring the negative 2 out front. We can say minus 2 e to the 2x. All right, and I have this x out front and an x squared on bottom. So this x actually cancels out with one of those and leaves you an x on the bottom. All right, and that is the derivative of x times e to the 2x power. All right, which I guess you could probably leave totally like that. Or you can realize that both of these have an e to the 2x. So you can rewrite that as e to the 2x, 2 over x, excuse me, times 1 minus 2 over x. Okay, I'm fine with either one of those answers. Just realize that that might pop up, and that's just, we've factored out the e to the 2 over x. All right, so you can pause and write that down if you need to. I'm going to go ahead and clear it out so I have room to work on the last problem. Okay? So the last problem, we got y is equal to 3 to the 2x squared. Again, it's exponential. All right, so we get y prime. Okay, or actually let me do a different notation here, just so you're familiar with it. Okay, we can actually say that the derivative of y with respect to x, so dy dx, is equal to, since it's exponential, I write down the 3 to the 2x squared power. Since the base is not e, then I have to put the natural log of 3. And then I need to take the derivative of the 2x squared, which would be what? 4x. All right, and then I might just rewrite this a little bit to make it look a little prettier. I might put the 4x out front, 3 to the 2x squared, natural log of 3. Okay? That way, you really don't have too much problem telling you, well, hey, what's inside the natural log, what's not inside the natural log. 3 is, 4x is not. And really having the x there, you really don't have too much of a hard time telling, hey, what's the base of the exponent? All right. And there it is. Okay, you might see the natural log out in front as well. Doesn't really matter. All right, now that we've done with exponentials, we need to talk about their inverse operations, the natural log. All right, here's a natural log function. Excuse me. And here's its derivative. All right, so notice that the natural log function is only defined when x is bigger than 0. So it starts right here. And what are my slopes? It's what? Very positive, still positive, just less positive. Okay, and it'll be less positive forever, and it'll actually, that slope will get closer and closer to 0. All right, so when I write the graph, the derivative function, I've got very, very positive and then less positive forever. Okay? So what does that function look like? All right, well, you might have seen it before. Okay? It might help us if we looked at it a little bit further zoomed out. Okay, that actually, the derivative of the natural log function is actually just one branch of this function. Okay, we call it the square hyperbola. All right, but you probably recognize that maybe is one of our basic functions that we should know, which is y is equal to 1 over x, the reciprocal function. And it's just the branch of it where x is bigger than 0. Okay, because natural log, I can't plug a number in here that's 0 or less. All right, so it brings us to this rule right here. The derivative of the natural log is 1 over x. All right, and then if we do the chain rule, if u is a differentiable function inside the natural log, then we do chain rule on it. We say, all right, well, the derivative of the natural log is 1 over the inside of the natural log. Okay, let me write that here. So just this part, the natural log, the outside part, gives you 1 over the u. And then since it's a differentiable function on the inside, you have to multiply that by the derivative of u, technically with respect to x. All right, but an easy way to remember it is the derivative of the natural log of u is du over u. Du over u, du over u. Something easy, stick in your head so you have it memorized. All right, so let's look at some examples for that. First one here, I've got f of x is equal to x times the natural log of x. All right, so we have a product rule. All right, we have an x times the natural log of x. So when we take its derivative, all right, we can say, hey, what's the derivative of x? It's just 1, so we don't really need to write it. Leave the natural log alone. Okay, so I'll write it here, 1 times the natural log, derivative of the first with the second left alone, plus, leave the first one alone, x, and take the derivative of the natural log, and you either have it memorized, which you should eventually, or you look back at the previous slide, derivative of the natural log of x is just 1 over x. All right, and technically we could use the chain rule on it because we can take the derivative of x, but what's the derivative of x? It's 1, so yeah, we don't even care about it. All right, clean it up a little bit, and we end up getting the natural log of x for the first part. And we have x over x, so that just turns into 1. All right, that's it. All right, let's look at the g of x. Okay, a little more complicated because we have not just x inside the natural log, we have x cubed. All right, but we have the chain rule for the natural log. So we take the derivative. Okay, we'll have put the inside on the bottom. Okay, because that's what the derivative of natural log does. It just puts the inside on the bottom. All right, and since the inside is not just x, we need to take the derivative of that. So the derivative of x cubed is 3x squared. All right, and we can clean it up a bit. We got x squared on top, x cubed on the bottom. So what happens? The squared cancels out. The cube turns into just the first power, and so we get 3 over x. All right, there's actually a different way to do that problem. Okay, if you remember some rules about natural logs or logs in general. All right, there was one of those rules that said, hey, if I've got a power inside the natural log, I can actually bring that power out front as a coefficient. All right, so this function here just turns into 3 times the natural log of x. Utilizing that natural log or that logarithmic rule that the exponent could come out front. And then we take the derivative of that. Now the 3 is just a coefficient. So we have the 3, and then the derivative of the natural log is 1 over x. And so times 1 over x, which when I multiply that together gives me 3 over x. Okay? There's really one's not easier than the other. Okay? You probably can go straight there once you simplify it on that one. Whereas that one, you'll have to cross some stuff out. Okay? Whatever you like to do there, doesn't matter. All right, and then my last natural log problem over here. Okay, there's not really a rule for that one. No natural log rule. I think we had one that said we have addition on the outside of the natural log. We could put it in as multiplication on the inside, but this is actually addition, so we can't do it. All right, so when we take the derivative of h, so h prime, all right, we'll put the u on the bottom, x squared plus 1, and take the derivative of x squared plus 1, which is 2x, and put it on top. That's simple. Do over u. Got it? Good. All right, so let's do a couple more problems here. All right, the concentration X, we got something about chemicals up here. A certain chemical after t seconds of an autocatalytic reaction, is given by this function here. X of t is equal to 10 over 9 times e to the negative 20t power plus 1. Show that x prime of t is greater than 0, and use this information to determine that the concentration of the chemical never exceeds 10. All right, so there's some stuff there, but really, hey, let's just find the derivative first. Okay, let's see if we can find this derivative. All right, so let's just do it. X prime of t. All right, we've got what? Quotient rule going on. Check and make sure I'm doing this correct. All right, sorry for the pause. The book would actually have us, instead of doing the quotient rule, which gets a little tricky, okay, a little more convoluted because you got low D high minus high D low stuff. So you can actually rewrite this thing. Sorry for the pause there, guys. X of t is equal to 10 times 9e to the negative 20t power plus 1 raised to the negative first power. Okay, so just bring the whole bottom part up as a negative 1 power. Is it more, I don't know. Quotient rule might have been better. Well, let's just do it this way since I've got it written. Okay, so when I do that, I've got a 10, which is the coefficient, and then now I've got a chain rule. Okay, so what do I do with the chain rule? I bring the negative 1 out front, so I can actually make the 10 become a negative 10. All right, I rewrite the 9e to the negative 20t power plus 1. Subtract 1 from negative 1, which gives me negative 2. And then I need to take the derivative of the inside. All right, with the derivative of the inside, the 1's really not going to play a role because its derivative is 0. We'll take the derivative of this 9e to the negative 20t power. All right, and if you remember the derivative for the exponential function, okay, we'll have the 9 because of the coefficient. We'll rewrite the exponent just as it is. All right, since it's the base of e, we don't need a natural log because the natural log of e is 1. And then we say times, and we take the derivative of that, which would be, or the exponent, negative 20t, which is negative 20. All right, so take a look at that. All right, so when I rewrite here, let's see what we got. I got multiplication, it's the parentheses, multiplication, multiplication. So really we can take the 10, or the negative 10, the 9, and the negative 20, and multiply them all together. Okay, that ends up giving me a positive 1800. That e to the negative 20t will be on top. And then we move this -2 back to the bottom, and that becomes 9e to the -22 power plus 1 squared. And that's the derivative. All right, now let's go back and tackle this problem. Okay? It said here, show that x prime of t is greater than 0. Well, how the heck are we going to show that? All right, well, let's think about it. Okay? If you remember what the exponential function looks like, okay, the exponential function will never, ever give you a negative number. E to a power, okay? Even though it's a negative power, technically brings it 1 over e to the 20t. All right, and so that'll be 1 divided by a really large number, depending on what t is. Okay, but again, that's just going to give you a positive number, so the whole top is positive, 1800 is positive, exponential is always positive. And then what do we have on the bottom? We can make the same rule here. We also have what? Squared. So squared, that means the bottom's always going to be positive. So if the top is always positive and the bottom's always positive, then the overall thing is always going to be positive, which is greater than 0. All right, now how can we use that information to determine the concentration of the chemical never exceeds 10? All right, so if the derivative is bigger than 0, that means that what? The slope is always positive. All right, so we got something what? Going up maybe like this, possibly. Okay, we could graph it and tell exactly what's going on. All right, but we could actually figure out, hey, what's going to happen as I go to infinity? Okay, after t seconds, going what, that way? All right, so since it's always increasing, it's doing this, so you would think at the very end, all right, it's going to continue to grow forever and ever and ever and ever. Okay, we just basically know my maximum is not over to the left, it's going to be over to the right if it has one. All right, so that's what this tells us. Since it's always increasing, its maximum is going to occur at the end. It's actually maybe not going to have a maximum. All right, and then we can say, hey, if it's going towards the end, all right, then really what I need to think about is what is the limit of that function? That original function, 10 over 9e to the -20t power plus 1. Okay? What is the limit of that as t goes to infinity? All right, well, let's think about it. If I plug it in infinity in, all right, -20 times infinity is going to be a really negative number, negative like 5 billion. All right, but the negative actually makes it a fraction, so this part would turn into 9 over a really large number plus 1. Okay, well, 9 over a really large number is essentially 0, so that gives me 10 over 0 plus 1, which is 10. So this tells me that the limit of this thing, as it grows forever and ever, okay, it's actually going to flatten out but continue to have a small positive slope. Okay, we know the maximum is never actually going to exceed 10. That's going to be its limit of growth on top. All right, I think I got one last problem here. Let me see. Yeah, one last problem. Okay, there are some functions we still don't have rules for yet. Okay, we've got a lot that we know. Okay, we've got any kind of polynomial, rational function we can do, exponential function, natural log function, trig functions we've learned. Okay, we haven't learned about inverse trig functions, which we probably won't. All right, but there's some that we can actually use a little trick. We can use rules of logarithm to help me find the derivative. So let's look at this one right here. F of x is equal to x to the x power. Well, what kind of function is this? Okay, well, it's not exponential, okay, because an exponential function has a number as its base, not a variable. All right, and it's not really a polynomial, a squaring function or cubing function, because the exponent is not a number. Okay, so it's kind of a hybrid of the two, if you will. All right, so we don't have a rule for that. Okay, we can't use the power rule because it's not a power. Power is x. All right, we can't use exponential because the base is not a number. All right, so we got to do something different. We got to use rules of logs. All right, and let's do this here. F of x is equal to x to the x power. All right, well, if you remember this from AMP, from Advanced Math Plus, when we solve equations like this, all right, if we want to get the x out of the exponent, what we can do is we can put a log in front of both sides. So I'm going to take the natural log of f of x is equal to the natural log of x to the x power. And why that helps is the logarithm rules tell me I can bring the x out front. So this turns into the natural log of f of x is equal to x times the natural log of x. I've gotten rid of the power. All right, and then now I can just take the derivative of both sides. Okay, so the derivative of this side, I've got a natural log function, okay, with a differentiable function in the middle of it. And so that derivative is going to be 1 over f of x times the derivative of the inside, which is f prime of x. All right, that's actually what we're trying to find is the f prime of x. That's this thing right here. Okay, so there's where it is. We'll have to do some manipulation a little bit. All right, and then the right side is going to be a product rule. Okay, and I actually think we've already done this problem. All right, product rule, what's the derivative of x? It's 1 times the natural log of x just as it is, plus, leave the x over there, take the derivative of natural log, which is 1 over x. And so we end up with 1 over f of x is equal times f prime of x is equal to the natural log of x plus 1. All right, we still want to find what the derivative of the function is, so because that's what we're trying to find, the derivative of this original function. Well, there it is. We just got this pesky 1 over f of x on there. And so what I can do is I can get rid of that by multiplying by f of x on both sides. So f of x, that looks like an f, right? On both sides, gets rid of over here. And so we have our derivative function, f prime of x, of that original function, x to the x power, is equal to the natural log of x plus 1 times the original function, f of x. And the original function, f of x, was this x to the x power, stuff in green up there. So we can rewrite it as x to the x power. And there is your derivative. Okay? Using a little bit of logarithm rules in order to help you out. All right? On the next page, you'll see the problems I want you to work and the link to this video. Have a good one. Test is going to be next Thursday.